Come on, let's do some Turing, man. So see how they all come in? See that? That is a belt well run right there, guys.
I think it's a really interesting question.
Yeah, yeah.
This is for which.
Yeah.
It's just that's a cool thing to think about.
It's very challenging to play neural network, and it's striking basically someone which is answer stability and the loss speed at which the loss indicates like.
Hello everyone. Well, we're thrilled to welcome Professor Zhiyuan Li from TTIC. He'll be sharing some long thoughts about short memory. Please welcome Zhiyuan.
All right. Thanks for introduction. So today I'm going to share about our recent work, which will be on arXiv in a few days, on chain of thoughts and about the size of the chain of thoughts. So this work is a collaboration with 3 awesome co-authors. Chen Xiaoyang is my first year PhD student at TTIC, and Nati is not here, but he's here today, and also David McAllister from TTIC. So I would like to start this talk with the following question. When is pencil better than pen? Answer? That's the right answer. so the answer of this question depends on very on scenario. In different scenarios, you can get different answers. For example, one thing I learned from the movie 3 Idiots is that if you want to write in space, you want to use pencil, because there's no gravity there, and pen does not work. But in this case, we like to focus on this situation. Imagine you go to a max exam without scratch paper, and that's really the situation, as Jinhong just said. Erasing becomes important. So obviously, there are a few issues of pen. I'm just going to list them. First thing is you can easily run out of the scratch space. For example, you can run into this situation. At the end of the exam, you realize you have a fantastic proof, but there's already no room for it. You used all the space in the exam paper by doing scratch. And another issue of pen, which is kind of induced by the first issue, is this also makes your progress slower. For example, it takes longer time to find useful scratch out of all the useless ones, right? It takes longer time to identify these useful things. And this also increases the error rates, because, for example, there are various reasons, and the most obvious reason is just you can copy the wrong number. And this is not only issues for pen over pencil, but more generally, this is about whether we can erase and rewrite. The contrast between erasable and non-erasable forms of writing, like pencils and pens, is something we encounter frequently in real life. Another example is the difference between CD-ROMs and USB flash drivers. Even today, we still use CDs for installing drivers and playing music in cars, where USB flash drivers are used daily for data transfer and storage. So by observing their usage, it is clear that non-erasable forms of writing offer higher data stability, meaning the information is less prone to tampering or accidental modification. Because since there is no need to consider future edits, non-erasable writing also provides better durability over time. And on the other hand, erasable writing is more space efficient, and we are suited for drafting, but not for a final or official document. For example, you wouldn't use a pencil to sign a legal document, right? And today's focus is another method of non-erasable writing, which people use every day nowadays. And it's a chain of thought of language model. And however, we will see soon, by the nature of chain of thought, which is like sort of like Scratch, it is not clear why it should be non-erasable. And so far, we don't have a erasable counterpart for chain of thought yet. So I would like to first briefly mention or like redefine what is chain of thought in this talk. So in this talk, I'm going to use chain of thought to refer to autoregressive next token generation of intermediate steps before the final answer of the problem. So this is slightly different from the original meaning of chain of thought, which refers to a prompting technique. This is first proposed in Weil in 2022, where they said that you should first give a few examples of questions and answers, and including the intermediate steps of the answers to the in the prompt, which you give to language model, and then you ask the real question. And in that case, language model can have better accuracy towards the original question. But here, we're just using chain of thought to refer to the fact that you're going to first autoregressively generate a sequence of tokens as intermediate steps towards the final question. We're not talking about prompting. And it is well known that generating the intermediate steps before the final answer improving reasoning capability of language model, both empirically, and we also have statistical evidence for that. And if you don't know what is chain of thought, then this is just a quick plot explaining that. You just do a forward pass, and then you generate a new token, and you append that to the current sequence, and you do another forward pass, and so on and so on. So it's chain of thought in 2025. So what's the difference here? I guess one important thing happens in the end of 2024 or early 2025 is that people have this new notion, which is called long chain of thought. And this is related to those models like OpenAI O1 and O3, and also Deepseek R1 and Kimi K1.5. So basically, people realize that if you use outcome reward to train a model with reinforcement learning, then this will encourage model to increase the length of chain of thought and also greatly improve the reasoning accuracy. And this is like kind of like a message from Deepseek R1 technical report, which is they're kind of like the first company to like provide open source model parameters. I mean, open source model with public parameters in this line of these models. And they're also explaining how they get their models by doing reinforcement learning. And in particular, there's an interesting phenomenon called aha moment, which refers to examples like this. So this is like a math problem, and the language model is asked to solve it, but somehow the language model got stuck and made a few failed attempts. And at a certain time point, the model realized, wait, that's an aha moment I can flag here. It realized some useful direction that it can actually make progress and then solve the problem. And this thing is not in the training data. It's kind of like learned by language model in the reinforcement learning with outcome reward. Okay, so previously we imagined like going to a math exam without scratch paper, but with pencil. Now let's like make analog and think about doing imagine planning with language model. There are a few examples. Like for example, you can scheduling courses, or just scheduling prospective PhD student campus visiting meetings, where you have constraints from both professors and from students, and maybe from like available offices, etc. And the common nature of this kind of like problems is that they can be written as a satisfiability problem. You can have a few like Boolean or discrete variables and write a formula like this and ask if there's a solution. And there's a exponential time hypothesis saying that for general 3 set with n variables, you can solve them with less than exponential n time. And that means we need exponentially long COT in the worst case if you want to language model to solve this planning problem. And this is bad because everyone knows that if you just use a naive algorithm by enumerating all the possible assignments of these variables, it takes O(n) space. So let me summarize the issue of long COT. This is similar to the issue of going to exam with a pen. The first issue is that you can run out of space, and COT length can go beyond GPU memory. And in reality, when we do inference, we need to use GPU memory to store KV cache of the previous tokens. And the memory you need is roughly embedding size times the sequence length times the number of layers. And let's do a concrete example, concrete calculation. For Llama 3.1, which is a 405 billion model, a single sentence can be long as 120K. For a single sequence, the KV cache would require more than 100 gigabytes memory. And this is more than like H100. And also this makes inference slower, even if it fits in memory. Because time spent on generating next token for current transformers and language models is proportional to a sequence length. And there are multiple considerations here. By saying time, I'm not only referring to work log time, but you can also measure it by like number of floating point operations you need to do, or like number of like in terms of IO complexity, like how many like bits you need to transfer to the L1, L2, L3 cache, which can actually does the computation from GPU memory. And the third issue is it also leads to worse performance. And there are various challenges for long context. For example, like attention dilution, or like you need higher precision, etc. Okay, so back to this table. So in this talk, we are going to talk and introduce a method which allows chain of thought to use less memory. And the way we do that is to introduce a reduction rule to allow chain of thought to erase. So we call our method pencil. And it is the first letters of pencil enables context-efficient inference and learning. So Matthew comes up with this excellent name. We like this name because it has this nature of erasing. If you erase this word and you get a pencil and it starts with itself, it's like recursive, right? Recursive function calling. So in detail, we add 3 special tokens into the vocabulary, which are call, sap, and return. They're kind of like motivated by like this idea in programming language, like stacking and function calls. And in a nutshell, pencil means to apply the following reduction rule whenever possible during the COT generation. So here, both C, T, A, they are strings. You can think C is like context, T is like thought, and A is answer. So when you see a return, and you can pass the current string into the following format, you are going to reduce the thoughts and only keep the answer. Append the answer to the original context. In detail, we have some restriction on the type of A and T. We don't allow step special token in A, and we don't allow call in T. So this parsing, this is unique. More specifically, you can think we are running this following detection algorithm every iteration after generating, after each time the language model generating a new token. So whenever a language model generates a return, we find the most recent step token, and then we find the most recent call token before step token, and then we pass the string into the following format if this both step and the call token exists. If matching, we apply the reduction rule to simplify the string. So that's it. That's a method.
Why erase? What? Like, how does this method erase the memory?
Oh, in this reduction rule, the thought T goes away. right?
We generated this open shape everything. I show you
Yes, that's true. That's true.
You do it a bunch of times. So you write stuff, you delete T. It's like automated backtracking. You do it over and over.
Right. So in the next few slides, I will explain a little bit more how we think with pencil, and later I will explain how we teach transformer to think with pencil. So this is the reduction rule, and a bit more explanation on intuition for these letters. So C means context, which embeds the upcoming subproblems to be solved. And for example, it can this subproblem can be in the form of like function to be invoked, and you want to know the answer, return the value of the function call, but you don't want to keep the intermediate steps to compute the function in memory. Those intermediate steps that you don't want to compute, don't want to keep in memory is called thoughts. So they're not useful for future reasoning. What you only care is the answer of the function, but not the computation in the function. And I want to mention that in this generation, in this process of having intermediate steps towards solving a subproblem, it's possible to have another core there. Like you can recursively call functions, as everyone doing programming, and this is totally possible here. And A refers to answer, which is the thing you really care about, the answer of subproblem. And this is useful for future reasoning, and you want to keep it. But it can be erased in the future. So next, I want to walk you through a concrete example to see how do we actually think with pencil. And this example is QBF, quantified Boolean formula. So it has this general form where you have like alternating quantifiers of exists and for all. And satisfiability is a special case of QBF where you only have exists but does not have for all. And we know QBF is p-space complete, which means it is the hardest problem solvable using unlimited time and space polynomial to input length. So how do we solve this QBF? A very naive solution is just solving this QBF by recursion. And like this is the code, you don't need to read it. But basically what you'll do is that you have this function which will recursively call self, which is QBF assign, solve QBF assign. Assign is like the partial assignments up to some variable. And solve QBF assign means if I fix my first few variables as this partial assignment, is the remaining formula true or false, right? And then this is a function that you will recursively call self to solve this problem. So initially your assignment is empty. And then depends on whether you have exists or for all, you go to two branches. If it exists, then you try first assign the current unassigned variable to be false and then see if it satisfies. If it satisfies, then return true. Else you just return the satisfiability of the remaining case. And similar for all. So this is a completely trivial program. So we want, so say like transformer solve this problem using this algorithm, using this stupid algorithm, then COT will require exponential length because you need to do this evaluation on each of the 2 to the n leaf node. Right? So you first go down this branch, like assign unassigned variables to just get a new value. And when you assign everything, you just use COT to evaluate the predicate, the truthfulness of the predicate. And we will show pencil actually can delete the intermediate computation in function calls after it returns, and therefore it only uses own memory, linear to the maximum length the pencil will have is linear to the input length. So in high level, this is so far is completely trivial, but we're just going to see how transformer, how we can use the previous introduced pencil rule to do this thing. So this is a concrete problem. You have 2 variables and you have 6 clauses. Those clauses are not very meaningful. They're generated in a random way. And on the right, on the left, I have model generation. And on the right, I have the sequence I got by applying the reduction rule. So this is the first step. By step, I mean I'm showing you the sequence I'm going to get until the first return is generated. And on the right-hand side, I'm going to show you what to get after this reduction rule is applied. So let me walk you through the sequence generated by the model until the first return. So basically what happens is the model first starts with the first quantifier, which is exists x2, and it tries to set x2 to be false, which is here. And then it's trying to solve the sub-question. Is it true? Is this remaining statement formula true after setting x2 to be false, right? And then it realizes there's another unassigned variable, which is 1, and then tries to set 1 to be false. And then everything is assigned. Then try to evaluate the truthfulness of the predicate with both x2 and x1 being false. And this part is done with this chain of thought. And then after chain of thought, you realize this predicate is false, and then it returns. So what happens with this reduction rule is everything between the most recent step and most recent call goes away. These are chain of thought to evaluate the predicate, and only thing remains is the answer false, which means if you set x2 and x1 both to be false, this remaining formula is not satisfied. So you got this. Does this make sense? So can anyone guess what's the next step? After you tried x1, x2 to be false and x1 to be false, what's the next thing to try? X1 to be true.
Doing the same thing as the code, no?
Yes. So actually here, it's not. You're going to return because this is for all x1. You already get x1 which is false, so you're not going to try x1 to equal to true. Just going to return. But actually, this is the idea. Here we just because we know this when x2 false, x1 false, this is false, so we're going to directly return to the upper level where you try x2 equal false, and you know it's false. And we can do so on and so on. And in the end, you got this. This is whole trace. I'm not going to walk through this, but this essentially is the program I showed before. Okay. So what's the question? The question is, we showed how to do this solve QBF with pencil, but this is with human. But can we teach this to language model? Right, that's the question. Can transformer learn how to use pencil in the following way? So the answer is yes. If you just train on this kind of like data, it will learn it. And we will show experiments later. All right. So the other thing is we showed how to do QBF, which is a specific type of problem with pencil. How about other problems? Is pencil universal? Do we need more complicated reduction rules to make it like more general? The answer here is yes, pencil is universal. Indeed, we can show pencil can perform universal space efficient computation with transformer by showing it can simulate Turing machine in a space efficient way. So this is the theorem. Basically, we can show that for any Turing machine, there's a decoder-only transformer TF, such that for all input token sequence X, pencil with transformer can simulate Turing machine with same total number of tokens as the runtime of Turing machine and the maximum context length as space used by Turing machine. And here we have some assumptions on the transformer. It's finite size and finite parameter precision, but it's infinite precision in the forward path. You can make it finite precision, like log precision, with some hard like stability, like perturbation analysis, but we're not going to do that. We just assume infinite precision, and we also assume you have average hard attention.
What is average hard attention?
Oh, good question. So in attention, you have in softmax attention, you have temperature, which is something like beta. And for each QKV, if you take the temperature to 0, the limit is hard attention. The instance was the limit of temperature goes to 0 is higher tension.
In that case, the softmax is just max.
Are just uniform distribution over all the argmax.
Okay.
So when we compare this to previous works, like previously people have shown that transformer is Turing complete, attention is Turing complete, which basically refers to this kind of like result. Like using the same assumption we have here, like people can show COT with Turing machine. COT transformer with COT can simulate Turing machine with same number of tokens as the runtime of Turing machine. And this implies that maximum sequence length is equal to runtime. So the improvement we have here is that we improve the maximum sequence length from runtime to space of Turing machine. And this is not these results and this idea also occurred in previous works, like this Pazel et al. 2021, which has a title "Attention is Turing Complete," and in another paper by Wei et al. On statistical meaningful approximation of Turing machine. And I also want to mention the connection between our work and Namir's talk on Tuesday. So in our work, we decouple time from space. And in Namir's talk on Tuesday about this theory of autoregressive time invariant autoregressive next token predictor, the description length of the model is decoupled from runtime. In that sense, you get better sample complexity regardless of your runtime of the model. But in our case, it's different. We're not decoupling description length, but we're decoupling actually space needs in runtime from the time needed in runtime.
Just about similar results to the second theorem. Is that what you mean?
Yes, but the difference is that in the Namir's talk on Tuesday, there's like more results about like sample complexity. Like this second result is not talking about sample complexity.
Yes, so I think we're just the Paresidol and Weidel are different variants of the Merrill result. They also only talk about time in that space. It's tools and exactly the architecture, what you count.
Okay, so I'm going to quickly go through the ideas behind how to simulate Turing machine with this autoregressive machine. Just standard notations. So I'm just going to give this a name like called autoregressive machine, which is basically just the generating next token. And this is like standard idea of how to show Turing machine can be simulated by this autoregressive machine. It does not have to be transformer, but just anything that iteratively generates next token. So the basic idea is that each step you're going to generate the new token which encodes the update of Turing machine, like which direction Turing machine head is going to move, like a new symbol written to the tape and new state. So this simulation is kind of completely trivial. And the previous works basically shows that this kind of simulation can actually be implemented by some transformer. And that's the kind of like the main technical contribution of these previous works, showing attention is Turing complete. Attention can simulate this autoregressive machine, which simulates Turing machine. So next time we're going to talk about how to using pencil to simulate the Turing machine in a more efficient way, memory efficient way. And the key observation here is that the description of Turing machine. So the description of the current configuration of Turing machine given by this autoregressive machine, which is a running trace of Turing machine from beginning to now, is much longer than what you'll need actually. You can actually summarize this Turing machine's trace into a much shorter string. And if you do so, you can make memory more efficient. And we're just going to apply pencil in a very special way, which is the following. We're going to set C to be empty string. You don't have any context. And we're also going to set A to be call and some T prime, the call special token, and T prime is another string. Just plug in, we get this. And in some sense, this gives you a mechanism to summarize. So you can run this autoregressive machine in this sort T. And when you want to make it a shorter string, you can generate sep and then generate call, and then generate another shorter string, which is T prime, and then return. Now you can just erase this T and make it T prime. And here we are assuming a standard summary of Turing machine trace T, which is just the, you kind of like have a very short sequence, just to construct a new Turing machine with the exact state as you would get by running the previous trace. So the T prime of T is basically the same as the memory, same as the memory used by the Turing machine in the current configuration. The number of the tokens written onto a tape. And basically the only question here is when do we summarize? And we have a few options. The first option is the trivial option, you never summarize. And the result is achieved previously. Basically, you have the same number of tokens as time. And for the same reason, because you never summarize, the maximum context length is just the number of tokens you generated, which is also time of Turing machine. The other option is you summarize every step. If you summarize every step, of course, the maximum context length is at most as the space used by Turing machine on its tape. But because you summarize every step, you are going to generate a lot of more new tokens, these summary tokens. This is like space times time. So the reasonable thing to do here is you summarize whenever you can halve the current sequence length. If you do so, you will still be able to control your maximum context length as at most, say, a constant factor times the Turing machine space. Because otherwise, it's going to, if you're going to use more than constant factor of Turing machine space, then you're going to summarize before that. And also, this we can show that the total number of tokens generated in this case is roughly just the time multiplied by some constant. So I'm going to skip the proof here. It's very simple, actually. Once you like write this down and think about this. So that's all about theory. So next, I'm going to talk about experiments. So theory does not answer all the questions. It shows that pencil allows universal space-efficient computation, but we don't know if transformer can learn how to use pencil. And we don't know if pencil is more difficult to learn compared to like its COT counterpart. And we would like to evaluate, answer this question by doing some empirical evaluation on some synthetic tasks. And in this work, we consider 3 tasks. The first one is 3 set. The second one is QBF. And the third one is the instant puzzle. And for each task, we design an algorithm which uses pencil to generate the train set. And we will explain what is the COT counterpart in the next slide in more detail. But in short, it's basically just the sequence of tokens generated by language model with pencil, including all the special tokens. And that's the COT, and you can train on it. So this is a concrete example. So this is the previous QBF example I showed you. On the right, there's all this generation and reduction process of pencil. And all those tokens in both font, they are first generated by pencil, by language model using pencil in this iteration. And what I do to get a COT, to get a chain of thought, is just concatenating all the both font sequences from each iteration, and I get that. So it turns out that COT is useful for transformer to learn to solve the problem. I can just do supervised fine tuning, supervise the training on that COT, and transformer is able to learn how to solve the synthetic tasks like 3 set, instant puzzle, and QBF. Right. So I also want to talk about instant puzzle if you don't know that. Basically, so first, this puzzle probably has nothing to do with Einstein. It's not clear why it has Einstein in its name. Maybe it indicates this requires some intelligence to solve this puzzle. But in a nutshell, this puzzle is basically a special type of satisfiability problem, but it is stated and solved in our experiments in natural language. So this prompt is the original puzzle you can try to solve. So for size n angstrom puzzle, the solution space is essentially n to the power of n squared. And in this case, it's a size 3 puzzle. And the solution space is essentially like this table. You have 9 entries, 3 by 3, and each entry has 3 possibilities. You basically want to satisfy all the explicit constraints from the prompt, and also the implicit uniqueness constraints, which is like each pet can only be owned by one person. Each person only owns one pet, these kind of things. These are implicit constraints. It's not in the problem, but it's indicated by the name angstrom puzzle. So this is a comparison between the maximum sequence length you will get between the trace of pencil and this COT counterpart of pencil, which is just concatenating all tokens generated by pencil. So in each subplot, we have the blue bar, which indicates the problem size, which is the maximum length you would have without pencil, which means without reduction. And the red one means the maximum sequence length you would have with pencil. And you can see when the problem size increases, the maximum length you would need it increases exponentially when you don't have reduction rule. And when you have reduction rule, when you use pencil, the maximum sequence length increases in like linear or polynomial way. So I'm also going to talk about the training objective before I actually show the convergence training loss curves. So we basically train a very small transformer, like smaller than 25 million parameters, using Adam with fresh samples per step. And we basically have a distribution of like instance, which is this P star, and we sample X from that. And Y is the COT generated by X following the preset like program. And theta is the parameter, and we use P theta conditional on X to denote the next token probability, next token distribution given the prefix X. The training objective of COT and pencil are very similar. So they basically require us to predict the same set of tokens, but based on the different prefix. So for COT, it's very standard, just given the instant problem and given the prefix of the solution, and then you predict the next token in a solution in a COT. And for pencil, the prefix is shorter because we have this reduction rule. And pencil predicts yi based on the remaining string after language model consecutively generate y1, y2 to yi minus 1 with pencil. So that's the only difference. The same model, same parameter, same architecture, same set of tokens to be predicted, but just different prefix. And because this 5xy to I minus 1 is shorter than the original string, because we have this reduction rule, pencil actually requires less flops per step in the training. And the same happens for inference. Now let's see some experiments. So now I'm showing the training curve, which is with respect to both accuracy and the loss in terms of number of iterations you have. So these are for QBF experiments, and n is equal to 5 and 6. So this red line is pencil, and blue line is COT. We can see from training loss, like pencil is slightly faster in terms of iteration, but in terms of like accuracy and trace rate refers to the average accuracy over the entire COT sequence. And this accuracy refers to the final accuracy. In terms of trace rate and accuracy, they're close. And for this experiment, we don't have a maximum context length for the model. Just because it's for 5 and 6, they're still not too long. So we are able to fit the entire COT sequence into the model's context window. And this experiment, same experiment, reported in terms of flops. Here, flops, we mainly care about the flops used in attention, because the transformer model is quite small, but the sequence length is pretty long. So the embedding size is very small compared to the sequence length. So most of the flops are consumed in attention layers, because when the context length becomes longer, the flops you need to generate next token in attention layer is like linear to the context length. And because of that, tensor trains much faster in terms of flops than DOT. So iteration was they're close, but flops they win.
Does that mean like tensor has less shorter context length? Yes.
So this is This is shown from these plots. You can see like standard COT will like exponentially increase in context length. So this is our observation. Convergence pencil is similar to COT in terms of steps, but faster in terms of flops. And we also try to scale up to like a problem size equal to 10. And in that case, it's basically just too long, and we are not able to fit into our GPU memory. And we somehow just set a maximum context length. So basically, you can see when this problem size gets very large, the COT will be longer than the context length, and the standard COT will fail to work. But tensor will still be able to get 100% accuracy, like even for this n equal to 10. And this baseline refers to just train with answer, train with problem and answer directly without any COT. So that's much worse than COT. Next, we're going to present some results for Einstein puzzle. So on the right, we have like comparison between COT and pencil for different sizes of puzzles. So we can see pencil consistently perform better than COT. And they can both get like almost 100% accuracy on 3x3 puzzle, but when the size grows, the performance of COT drops. And on the right, we did some ablation study on the context length and parameters you have for the transformer. And still the message is similar, pencil always outperforms COT. And it can work with much smaller model, like even 3 million parameters. And this is for 3x3 Einstein puzzle. The observation here is that pencil achieves better test accuracy than COT, and even with like less parameters or like less context length, or for more difficult tasks. Okay, so now I would like to summarize a bit. So in the beginning of slides, beginning of the talk, we talk about like issues of like long COT, and in contrast, we have these benefits of pencil. So the first thing is, of course, reduce the context length. So it reduces the context length from the time complexity of the problem to the space complexity of the problem. And this also makes training and inference faster, even without hitting the context length limit. And this is because the time spent on generating next token is proportional to sequence length. And we also get better accuracy. So as conclusion, we propose pencil. So this is basically autoregressive generation plus reduction rule. And the goal is to reduce the maximum context length of COT, of a context length in transformer or language model reasoning. And we show pencil allows transformer to do universal space efficient computation by simulating Turing machine with the same time and space complexity. And we also show that context length reduction can make training and inference more efficient in flops and also like input-output complexity. And we get like impressive like test accuracy, which is 97% on Einstein puzzle with only like 25 million model and the 2000 context length. So have some extra statistics about the like workload time to solve the problem. For 5x5 Einstein puzzle, like our current code, which is not like fully optimized, it doesn't even use KV cache, but it is able to solve the Einstein puzzle in like 40 seconds. In contrast, GPT-4 we tried, it solved the problem in like 30 seconds with the wrong answer. It writes the code, and the code basically generates the wrong answer. And O1 is able to solve the problem, but it takes 8 minutes. And GPT O3 mini high is also able to solve the problem, and that's much faster than O1, but it still takes like 2 minutes. And I think if we do KV cache, we can be much faster here, basically because each time like for the pass, it takes like currently it takes square time instead of like linear time. A bit of like ongoing follow-up works, like something we're thinking about doing, like simulating RAM instead of like Turing machine, which might be more useful. And currently, our data is generated in a case-by-case way, and we probably want an interpreter automatically convert trace of Python code to like data of pencil. And special cases like universal prompting, like you have a Python interpreter which takes the Python code as input and outputs the result. Also, like a pure function covariant of pencil. Basically, you instead of have one transformer, we can have multiple transformers, like a stack of transformers. Each time you ask a question, you push the question, you create a new transformer in the bottom of the stack, and you solve the question there, and you get an answer, and you return the answer, and you delete that transformer, and you put the answer into the top language model. So the hope is that it probably will have like better learnability or even like better length generalization. Some future directions. One thing interesting and seems important is to have a better implementation for this training on this tree structured input. So for our current training data, which is like we generated for pencil, it's not like chain of thought. It's like tree of thoughts. You have different branches, and you delete and you recursively. It's really like a tree. We have an input tree as opposed to an input sequence. We want to have efficient way to do forward and backward pass on this kind of input, tree structured input. In theory, it's completely trivial, but not sure how to do it efficiently with current existing hardware. So in some sense, we need to solve this issue with like you have multiple subsequences which share the same prefix, and don't want to do like a multiple forward and backward pass for the shared subsequence. And another interesting idea is to say teach Deepseek R1 to use pencil to make like this to solve this issue of like having too long COT. Maybe you can teach them by some instruction tuning and another round of like outcome reward based RL, like with some length penalty and using special tokens. Of course, the question is like not trivial. Like how do we get instruction tuning data with pencil? I don't know, but there's just like random thoughts. Maybe we can turn some search tree in Ling into pencil training data, because you have in Ling you have this math proof like tactic and like transfer this state into another state, like this kind of thing. Maybe in general, like some running trace of Python program or something could suffice, but I don't have a good idea until I try it actually. Okay, this is the end of that talk. Thank you.
Will we have time for any questions? Why don't we start with Danica?
So I just want to make sure I understand. In the examples you're showing, you're doing pure language modeling, right? Like you give it the execution trace basically, and you say model this. So when you have better accuracies for pencil than for COT, That's only because COT hits the length limit and then things start breaking, right? Otherwise, they're solving exactly the same problem. Is that true? Or COT can get distracted by some of the stuff that got deleted, I guess, also.
Right. So in our current experiments, the answer is yes. But I suspect if you have unbounded memory, and when this problem instance gets really large, there might exist a situation where you can still get better performance from Pencil because of other reasons, like, for example, your transformer size is bounded. Let's see this case. Like, this is 3x3 transformer. Sorry, this is 3x3 Einstein puzzle. And in this case, it's not that long because you see, when you have context length of 2000, COT is going to get 100%, like very high accuracy. But the performance drops when you reduce number of parameters. But Pencil still works in this case when you have 3 million parameters. So there's another reason, not just because context length.
So what is happening there? Is it that the attention in the COT, it's incorrectly attending to some stuff that Pencil had deleted?
Might be, but we don't really look into that.
Because other than that, like, what's the difference, right?
That's a good question, but I don't have an answer.
Okay, thanks. Also, if no one else is urgent, could you go back to like slide 6 or something when you had the Deepseek example? With the aha moment. All right, I guess it's after this. It's when you had this is an aha moment thing from Deepseek. Yeah, here. This equation is wrong. When they say first, let's square both sides, they have a sign error there. It should be x squared minus a, not a minus x squared. I guess it doesn't matter because they're going to square it again. But this is indicative of like one of the drawbacks maybe of this pencil approach is that like if you screwed up inside solving your subproblem, it's unfixable, right? Whereas if you can still look inside it, then maybe you could realize, oh, what I was doing there was almost right, except I made a sign error here, right? Potentially.
Right.
So I wonder whether there's a way to do something pencil-like that maybe uses, maybe I'm just saying this because I've worked on sparse attention, but maybe there's some way to do like a sparsifying thing rather than actually deleting the context. I don't know. This might be an idea to think about.
I'm not sure if I understand the question, but let me try to summarize. Your complaint here is that if there's some mistake happens in the reasoning process, there's no way to fix it.
Well, it's not that it's literally impossible to fix, but it's harder to fix if you
It's
this subproblem. Your final answer to the subproblem is wrong.
I see.
If you realize later that it was wrong, like if you were actually doing this on paper, you could go back in and see, oh, I made a mistake here, and here's how to fix my answer to this subproblem. But if you don't have that work anymore, you can't do that. Right? You have to do it again.
Right. So that's a good question. So you probably, in that case, you would like to redo the proof to see if it's wrong.
Maybe. I think if you were doing this on paper, right? Like what I would do at least is I would look back, I'd say, oh, it seems like something was wrong here. Let me look at what I did. And then I find the mistake and then I fix the mistake without having to redo the whole thing. Right.
That's fair.
I think that's roughly what you're saying, right? When we do something, right, we work on something, we work in a lemma, and then we figure the lemma, and then we don't actually, okay, we work in a whiteboard, we erase the whiteboard, and then regret it later, but when we put the paper aside and we ignore it, but we can, if you want to later on, we said, oh, we got something that's actually the wrong way, there's probably a sign error in this lemma that I proved, I go back and dig out that piece of paper that I opened and didn't throw to the trash can. So you don't want to throw that piece of paper in the trash can, you just put it on it, right? So I don't know if sparse attention, the problem is sparse attention like doesn't tell you what to attend to.
Right, so just plain sparse attention wouldn't do it.
Right,
but maybe there's a
what you're saying,
control.
this is what you're saying is this is equivalent to zeroing out the completely masking out the attention to those parts that were deleted. And that's just equivalent, like exactly. Sure. Right? And what you're saying is instead of zeroing out, maybe you can just like significantly downweight
Maybe.
or downweight
Yeah.
or something like that. But now to get the computation benefits, you have to be smart about how to implement attention. Just like when you have some things that are only secondary. I think that's maybe.
So I think
So I was confused about.
So I think the whole point here is what is the reduction rule. So for your theory result, it was very clear to implement Turing machine, what would be the reduction rule. But in the case of like your experimental studies, like for this Einstein puzzle or QBF, like what exactly is the reduction rule? Like, is it like something which is learned by the transformer?
No, this is the same reduction rule.
Okay.
It's always this.
So you explicitly generated this data.
Yes.
Oh, okay, okay,
Yes.
okay, sure.
Yeah.
Also, when you say you generate like pencil data, what does it exactly mean? Because your data is the entire COT. Are you saying you will just have these tokens?
Right, but you
embedded
train on
within your
different things,
data?
right? So
Yeah.
that's the 1 second. How do I jump fast?
You put these extra tokens where it specify when to reduce and when to not reduce. Is it what pencil data? Does that what pencil data mean?
You think the data is the same as COT, but you just decide to train on different prefix.
So this fee is like part of your inference process, but your data has to be like your data is just like chain of thought data. So I don't know what.
No, fee is part of the inference, but it also, I mean, when I say defines the data, actually I mean defines the training loss for pencil.
Okay.
For transformer that you're going to train pencil. Define training law that I'm going to use that to get the transformer parameters. And this is the training loss. And this fee here is basically exactly the like a rule like you would apply in inference. And you can imagine you starting from X, iteratively generating Y1, Y2, Y3.
Mm-hmm.
And after generating each YI, you apply fee. You apply this pencil's reduction rule. Like if you have a return token in the end, like you're trying to match, and then you erase the thoughts. You do this for each time. Each time you generate yi, and then you got this phi x y to the I minus 1.
Okay.
Does that make sense?
Almost. Yeah.
In terms of, can I answer in terms of your talk? I mean, so in terms of your talk, you had the F, which is.
You have a base generator that takes a prefix, takes some strings and then generates a single token. And then you wrapped it, you turn it into this generate concatenate thing. Like I don't remember what your notation was, but like F tilde, F just returns a token, and F tilde actually returns the string composed of the concatenation of the input with a new token. So the only thing is you replace the F tilde, you have to find the same F, but your operation now, instead of generating and appending, you generate, append, reduce. Okay. And everything else is exactly the same as in your talk. Right. So I mean, what you have at each time is like, so what you have after T iterations is not like T generate, append, generate, append, generate, append, but T generate, append, reduce, generate, append, reduce, generate, append, reduce.
And this is what creating this data, pencil data. Okay.
You have the same sequence of tokens being generated, but what you have is actually different.
So yeah, but okay. So are there like any better kind of reduced rules that like Danica was pointing out, like which is not like yeah, sure. I think this is already discussed, but yeah.
Yeah, that's I don't have a good answer to that.
Yeah, if you're removing the chain of thought, then how good of fixing this is?
Yeah, I mean, like here in this example, language model have like perfect ability to learn the like underlying program. So like at least for pencil, there's no issue. They don't make mistakes.
Yeah.
But if they make a mistake, it's actually not even clear to me how to enable transformer to have the ability to automatically discover their own mistake and correct it. So that's kind of like seems a bit far from here.
Also for real data set, like do you think, so I think intuitively, if I think like the coming up with this chain of thought itself is like much harder task than trying to figure out when to erase or when to keep this paper aside. So this reduction rules, do you think they can be learned by transformers based on which things that they had to pay attention to, or can this be a part of transformer?
Yes, this can be part of transformer. I think, sorry.
But in your experiment, it isn't right now, right? Your experiments are explicitly invoking this.
Experiments so far, they are not. They're just like learning from like instruction tuning. But I think it seems not very difficult to teach them with some instruction tuning and then do another round of reinforcement learning. And if you do like lens punishment, there's motivation to use a shorter punishment on the maximum lens.
Why don't we take all the other questions offline, and let's thank Zhiyuan once again for the lovely talk.
Thank you.
So now we'll have a half-hour break, and we'll come back sharp at 3 for Nadi's talk.